Hello, everyone. We can't wait to tell you more about our very informative and fun journey with developing Clueless game. To witness its transformation from the paper to actual implementation is pretty amazing. Today, our A team came together to walk you through our skeleton increment development. Each of us will take turn to tell you more about what we did for the increment cycle. I have Anthony, Fritz, Jonathan, and Rem with me. First, let me quickly go over what we have done so far. For our game, we have implemented client-server architecture. For the server part, we set up AWS server and an account for our A team, and also configured networking between our local devices with AWS. First, we'll talk more in depth on what we did on later part of the presentation for AWS server. We used Python 3 socket to develop client, server, and a game code that could pass messages between server and a client, and also store state information from message to client and a server memory. Anthony will demonstrate more on how this module works together in a later part of the presentation with his demo. Next, I will hand over to Jonathan to discuss more on our game subsystems.
Within Clueless are 4 hierarchical levels, but across Clueless are 2 parallel level 1 through level 3 subsystems. These subsystems compose the client and server subsystems, and these subsystems communicate. In doing this, online communication is enabled, empowering players to act and manage their gaming experiences. Plus, using Python client code, a stable network connection shall allow contemporary grade and contemporary quality entertainment. These compose the client subsystem. Within the server subsystems are player empowering and professionally powered technologies. Within the server game controller, game pieces, and game rules, but game state management, Clueless offers an authentic Clue experience and A-team courtesy. But utilizing the AWS server, the Python server code, and a custom-made network, the infrastructure offers a strong cloud solution. Thank you for viewing. This section was a brief subsystems report. I am Jonathan M. Kelly, but now I am introducing my team member, Fritz Wesselhoft. He shall discuss the game architecture.
Hello, my name is Fritz Wesselhoft, and I am a part of the A team. For this segment, I will talk a little bit about the game architecture or the different pieces that we have used in order to build this project. For the skeleton of the game, we are using AWS, which is Amazon Web Services, to provide the infrastructure that we need in order for us to build the game. We have chosen AWS because it's huge, it's very reliable, they're all over the world. So it seems like a good fit of something that we can use for this project. It provides a secure, reliable, flexible, pay-as-you-go, and easy-to-use environment. We can use AWS to deploy pretty much any information technology infrastructure that we want, such as servers, databases, network containers, and so forth. So specifically for this project, we have used a few components. The first one is the AWS EC2 server. This is just a normal server, a virtual server though, that is running Ubuntu 18. Another component that we are using for this project is a routable IP address. We will need to have a game server that is accessible for everybody. So we have given this server a public IP address, so everybody from the members of the A team and also the game testers can connect from anywhere they are, as long as they have an internet connection. Also, we are using a public subnet. This is just the place where we are hosting the server. The server has to be publicly reachable, so we need a public subnet where to put it. And the last two elements used for this assignment is some inbound rules. This is like firewall access because the instance is public. We don't want everybody in the world being able to reach it. So we whitelisted only certain IP addresses for the members of the A team. And finally, we also have a few accounts. We created an account for everybody, every member of the team. And the goal is that we can all access AWS, we can stop the server, we can, make changes if we need to, just make it a little bit easier for all of us to work together and, collaborate. And finally, this is the client game server access representation of the architecture. So we will have a client that tries to connect to the server. He passes some kind of credentials, most likely username and password. So the server will verify that this person is indeed authorized to access the game server. Based on that, it will be redirected to the game itself, or it will be prompted to ask another set of credentials if the user and password are not recognized. Thank you.
Next, I will pass the stage to Ram. He will talk a little bit about the game subsystems, their interconnections, and their interfaces.
In this diagram, we show the level 2 and 3 subsystems and the interactions between them. On the far left, we have the user, then in the middle, we have the client device, and on the right, we have the server. Around each of the level 2 subsystems, we have the level 3 subsystems. User state management, user actions, and client Python code for the client device, and server Python code, game state management, and game code for the server. The interactions are user I/O and I/O processing as the input gets passed from the user to the client device. Reads and writes to and from memory as the client device stores and checks state management, and the execution of Python code as logic is performed on this information. On the server side, we have a similar setup, with reads and writes to and from memory for state management of the whole game, and server Python code, which manages the infrastructure of the server. We also have game code on the server, which is a combination of all the parts of the game logic, including the rules and pieces and the like. Between the client and server, we are using TCP, IP in both directions. Here we attempt to lay out how a demonstration of an accusation shows each of these subsystem interactions, noting how the colors map back to one of each of the 11 items on the list from the previous diagram. During a sample accusation, the client code produces a list of options from memory and displays it to users. A selection is read in from the keyboard, input to a variable in the code, representing a choice, and is then stored in memory. After being processed by the client code, it is sent to the server over TCP IP. The server stores this choice in memory. The server Python code then reads the choice in from memory and processes it. According to the game logic, the server code will determine if the choice was correct and send a message back to the client to share the result. And now Anthony is going to walk us through the code and files for the skeletal increment.
Hey guys, my name is Anthony and I'm going to be demoing our game. On my screen you can see 4 terminals open. One is the server and the other 3 represent the clients. If you start up the server, for now you can see that the server actually shuffles and picks out a winning suspect card, a weapon, and a room card. The other players currently can't see what these answers are, but this is just to test out the game. So now if I go ahead and run the client script, I can connect to the game. I'm just going to enter my name for now. So as you can see, the server shows that Anthony actually has connected to the server. Then if you run each other, let's say enter rem, each other client script, you can also connect to the server. Once there are at least 3 players connected, you will see that the first player will automatically, for now, get assigned as Miss Scarlet. So as per the traditional rules, they will go first. So now the other players are currently waiting for that player to end their turn. So let's say I decide to make a suggestion. For now, it just prints out you made a suggestion and it ends your turn. Then it moves on to the next player. So let's say this player wants to make an accusation. They would get prompted to pick a suspect. For now, we're going to just pick Mr. Green, which we know is wrong because the winning cards are Mrs. Peacock, Candlestick, and Ballroom. So let's say we hit that. Then we choose a weapon. We'll just choose 0 again. And a room, 0. You'll see that it says your accusation was incorrect, out of the game. Now, this player can no longer make moves for now. Later on, I will implement them to be able to provide and disprove suggestions, but for now, we'll just kick them from the server. As on here in the server client, you can on the server script, you can see that they're disconnected, and then it's back to the next player's turn. So let's say this player wants to end their turn. It would hop back over to the other player. There's only 2 players left in the game. So let's say this player now wants to exit the game. Hit 5. It would print out the message, exiting the game, your turn is now over, and they're out of the game. Also, you can see from the server code on the log that the player got disconnected. And then finally, the last player remaining wins by default since everybody else either left or made an incorrect accusation. This is our demo. I hope you guys enjoyed it, and thanks for watching. Here are a few bloopers of us attempting to play the game on the AWS server that you might enjoy.
All right, I'm connecting now.
Go. All right, my turn first. What should I do? Just gonna get this wrong on purpose. So I'm out.
Oh, here I'm up. I'll move.
All right, that's asking to want to make a move.
I'll make an accusation.
Cool.
Oh, you got
From everyone in the A team, we thank you all for watching.